Okay, straight into it then. You're going to need your own paper, of course. Sorry about that, but I've done my best. All right, which diagram represents a heterogeneous mixture? So a heterogeneous mixture is two or more substances that combine together, and they each retain their individual properties. And if you take a sample of the substance, it may or may not have the same ratio of the components as another sample. So a heterogeneous mixture, I just think like vegetable soup. Homogeneous mixture, I think like seawater. Every sample of seawater has an identical composition. So what's the best answer here then? So this one's out. That looks like an ionic compound to me. This isn't a mixture. It's just one sort of diatomic molecules. And so that leaves that and that. So heterogeneous means hetero means different. So I'm thinking it's probably this one here, A. Ooh, and indeed it is A, leaving this to be a homogeneous mixture. Okay, question 2. Keep the SO4s, keep the sulfates together. Don't split those apart. That would be crazy. All right, so I've got 3 sulfates on the reactants. So I fixed the sulfates now. I see that there's a 3 for the barium here. So that's 3 for the barium there. That gives me 6 chlorines. So if I put 2 there, is that it? Did it just work itself out? That's not too bad. Ions balanced, chlorines balanced, sulfates balanced. So it's 3, 4, 5, 6, 7, 8, 9. So the answer 2 is D. 2 is D. 3, if it's a hydrocarbon, it's just made of carbon and hydrogen. This is an empirical formula question. So put the percentage over the molar mass and put the percentage over the molar mass. How many 12s in 75? 60. So is that about 6? 6 12s, 72 plus 3. Is that 6 1/4? Oh, that's evil. And that's H25. Divide by the smallest, which is 6 1/4 and 6 1/4. So that gives me C1H. That should be a quarter, sorry. Oh, that's 4, isn't it? 6, yeah, 12 and a. Ooh, so C1H4. So I reckon that is 3D. 3D. Nice. Ooh, tricky without a calculator, eh? Question 4. PV equals nRT. So you've got to remember that every graph looks like that, except for P versus V that looks like that. So which graph would not show a linear relationship? Oh, there we go. So P versus V, because everything else is going to be this graph here. So P versus V. So 4's A. Is it? 4's A. Nice. 5, some isotopes. 1-to-1 ratio. So I've got bromine 79.9. It's a 1-to-1 ratio. What are the stable isotopes? So for A, it's 79 to 81. So if it's a 1-to-1 ratio, the average is going to be about 80. That's pretty close. If for B, it's 80 and 81, so the average would be, if it's a 1-to-1 ratio, 80.5. No, we're looking for 79.9. C, 78 and 80, so the average would be 79. So it's not that one. I think it is A. And for D, 79 and 80, 79.5. Yeah, so it's A. So 5 is A. Because the weighted average, where it's weighted 1-to-1 between those two numbers, is 80. 5 is A. Nice. 6. So they love chromium and they love copper, because those are the 2 exceptions. Let's go to the periodic table. Chromium and copper are the exceptions. So which one have we got here? Chromium. So you're tempted to go 3D1, 3D2, 3D3, 3D4, but no. It's argon, 4s1, 3d5. So you can either learn that, or you could go back to first principles and you could say, well, I thought it was going to be 4s2, 3d4, since it's the fourth one along, chromium. But one electron goes from here over to there. A half fill 5d, a half fill any d is going to be stable. So 3d5, that's going to be stable. Just remember it. So that's going to be 6c. 6c. Seven, bismuth. Bismuth has the highest atomic number, and once past bismuth on the periodic table, everything's dangerous. So bismuth is the last safe thing that you can handle. Of course, some stuff before bismuth is dangerous, fluorine, but everything after bismuth is dangerous. Alrighty, so let's find bismuth, 83. Bismuth is 83. It's there. So it's period 6 and group 15. Period 6, group 15. Period 6, group 15. Period 6, group 15. So principal energy level number, well, that's just period. So that's going to be 6, period 6, and group 15. So that's D. 7 is D. They're trying to see if you've remembered to add 10, because it was the old group 5, but it's the new group 15. Alrighty. They said that question 8 was very disappointing. Typical characteristics of metals. Now, metals hate electrons. That's a big characteristic of metals. So many of their properties come from the fact that they hate electrons. So where are the metals? The metals are basically these. You could argue about hydrogen. These are the metals here, those ones. So they hate electrons. So ionization energy, that's the energy required to remove an electron from the gaseous metal to make a 1+ ion. Well, that's going to be really easy. Metals hate electrons. So we're going to have a low first ionization energy. And electron affinity, how much do they love electrons? Affinity is to love. So they don't love electrons at all. They hate them. Metals hate electrons. So the ionization energy should be low. And the electron affinity also should be low, 8A. 8A. Come on. 8A. Okay, increasing the order of boiling point. This question comes up every year. So you're looking not for the bonds within the molecules. That's all covalent bonds. No, that's not boiling. That's wrong. You're looking for the bonds between the molecules. So you're looking for a bond between that one and that one, or that one and that one, or this one and that one, etc., etc. Looking for the bonds between the molecules, the intermolecular forces. Alrighty, so let's have a look. Is it easy? So this is the weakest one. That's just London dispersion forces. It has no dipole. That's butane. And it has no hydrogen bonds. So that's the weakest one. Is that enough? Well, that just narrows us down to A or B as the weakest one. This is the strongest. How do we know? Because in A and B it's always the strongest. So I just have to put these two. Well, this is going to be the second strongest. This has hydrogen bonds. So whichever one has this second strongest is correct. So that's going to be B. So 9 is B. Just as a little point of order, this also has hydrogen bonds. So why does this acid have a higher boiling point than this alcohol? Well, because there's extra mass from this oxygen here. And there's a cheeky bit of ionic bonding going on as well when that hydrogen drops off. So that oxygen there, more electrons, more London dispersion forces. Ionic bonding's a stronger intermolecular force. Question 10, which does not have resonance structures. Well, my advice to you is to just learn these structures. Don't try and draw them out from first principles. But this is benzene. So that has 2 resonance structures. Those single bonds and double bonds exchange positions. The ammonium ion, well, that's only got single bonds. Don't forget, for resonance you need single and double bonds. So that's your answer there. B. The carbonate ion, oh man, there's 3 resonance structures for that. Don't forget the square brackets and the 2 minus. And ozone, well, there's 2 resonance structures for that. So you're looking for single and double bonds next to each other. So this just has single bonds. So why would they put that one in then? I think they put that one in because it has a dative covalent bond, maybe, to try and trick you. Didn't trick me. Question 11. Ionic compound. So ionic compound, I think, well, what's the most common ionic compound? Sodium chloride. So I know salt, I know the properties of salt. Let's see if that fits. So melting point, yeah, it's high. It's really hard to melt salt. You can't even melt it on your gas stove at home. So that leaves me with A or B. It's ionic bonding, strong forces, strong intermolecular bonds. You could argue if it's intermolecular, but strong bonding. Electrical conductivity as a solid is low. So the answer is B. Salt doesn't conduct electricity as a solid. For anything to conduct electricity, you need freely moving charged particles. And the salt, because it's a solid, they're not freely moving. I've got the charged particles, yes, I've got the positive and negative ions, loads of those. But, so how could you make them freely moving? How could you make salt conduct electricity? How could you make those charged particles freely moving? Melt it, dissolve it in water. So 11 is B. 12 is the least discriminating. You're smarty pants, you've no idea what's going on. Doesn't matter. Everyone had trouble with this question. It didn't discriminate between the stronger and the weaker students. So strong metallic bond. So think about group 1. Group 1, you've got lithium, sodium, potassium, and all the way down here is francium. Now francium they think's a liquid. They've never made enough to find out, but it's a liquid. So if you can just remember that, the bonds get weaker as you go down. The reason, this is quite a convoluted question. So sodium ions are +1, they're quite tiny, with electrons in the delocalized sea of electrons. Francium ions are +1, so it doesn't matter about the charge then, but francium ions are much bigger. So these have a low charge density, which means they're not very attractive, and the lithium has a high charge density, which means they're much more attractive to the electrons in the sea. So what is it about this that's making them such a low charge density? That's an endless question. So charge density is proportional to charge over volume. Charge over volume. So the charge is the same, the volumes, this is the bigger ones, the francium's the bigger one. So what corresponds to a strong metallic bond? So high charge, low volume. Large charge, so it's B, 12 is B. You could also think, so what's got really strong metallic bonds? Something very small, something with a very high charge, so that would be the aluminium 3+ ions. Aluminium 3+ ions are very tiny, and 3+ is quite a high charge. Alrighty, enough babbling, Thornley. 13. We'll have trouble with these questions. This one. So I've got equal masses X and Y. Equal mass X and Y. Absorb the same amount of energy but this one goes up by 10 degrees C, and this one goes up by 5 degrees C. So you've got delta H, or let's say Q, because it's not per mole. So Q equals MC delta T. And so delta T equals Q over MC. So delta T is the change in temperature. Q is the same. They said it's the same amount of energy, and the mass is the same. Okay, so that gives me the change in temperature is proportional to 1 over the specific heat capacity. What does that mean? As one goes up, the other goes down. So since this one got twice as increase in temperature, it must have half the specific heat capacity. The specific heat capacity of X is twice that of Y. So that's 13A. 13A. My God, I haven't got one wrong yet. Question 4, even a highly trained chimp could get this one right. It's the least difficult question. Hess's law. I like Hess's law. I think it's quite clever. I'm surprised. This is quite tricky. 3 equations. Okay, so I'm trying to get this one, the target equation. And nothing needs doubling, because looking at the answers, there's no 2s or 3s. It's just X, Y, Z. But something needs flipping around. Which one am I going to flip around? I like the hydrogen on this side because it's on that side. That's fine. And I like this on this side, this ethene, because it's on ethene there. So, yeah, this ethane needs to go on the other side. So I need to flip this one. I'm not even going to bother adding it up because looking at the answers, it has to work. There's no doubling or tripling. So if I did flip that, that means I changed the sign. What do I do now? I just sum everything. So it's X minus Y plus Z. X minus Y plus Z is D. 14D. Easy. Everyone could do that. 15. What's correct for that reaction? So I've got an exothermic reaction. It's going to be this profile. There's a reactant. There's the products. Delta H is going to be negative. And this is my EA for an exo. Right, does that help? So anything with low energy is stable. So anything down here is going to be stable, low energy stable. And anything at the top here is going to be less stable. Or maybe we could say, yeah, less stable. Alrighty, reactants are less stable than the products. No, reactants are more stable than the products, and the reaction is exothermic. Reactants are less stable than the products. Yeah. So the answer is D. The reactants are less stable than the products. They're higher up. And it is indeed exothermic because delta H is negative. 15's D. Nice. Man. 16. So how can you monitor rate of reaction? Well, you've got temperature change, colour change, pH change. You could monitor the change of volume of gas if you keep temperature and pressure the same. You can monitor the change of pressure of gas if you keep the volume and the temperature the same. Blah, de, blah, de, blah. Alrighty. So what have we got? I is the change in volume. Well, you're not going to be measuring the change in volume because that only works with gases. So that one's wrong. Is that enough? The I's wrong? Yeah, the answer's C. Boom. Next question. Double check. Yeah. Oh, there we go. I feel quite smart. So change of volume only works for gases. And those are not gases. Solid, solid. And these are solutions. Now maybe the volume of the solution does change, but nothing that you could measure using regular equipment. 17. How do I make calcium carbonate and hydrochloric acid go faster? Increase in temperature. Yep. If you increase the temperature, you increase the rate of reaction. More collisions per unit time and more energy for each collision. What about if you increase the concentration of the hydrochloric acid? Yep, if you increase the concentration, there's more collisions per unit time. So 1 and 2 is correct. Increase the particle size. Oh, people get this backwards. If you increase the particle size, you're making it bigger, making it more lumpy. That doesn't work. You have to make it less lumpy. You have to decrease the particle size, which increases the surface area. So a big particle has a small surface area, vice versa. So pay attention to that. So the third one's wrong. So it's just 1 and 2. So that's A, 17A. 18, oh, I have to work this out from first principles. So for the following reaction at the same temperature. So what have they done? It seems that they've flipped the reaction. They flipped it round. Reactants have become products. And it also seems that they've halved the reaction. God, I'm trying to remember back to my own video. Oh, hey, if I flip it, then I've got to put 1 over Kc. And if I half it, then I have to take it to the square root. I think that's what you have to do. So it's going to be 1 over Kc square rooted. Is that an option? Oh, I don't know if that square root can just go like this, 1 over root Kc. I think it must be able to. It's the only one with a square root, so it's B. So 18B. 18B. 19, what's basic? So basic is, so 19, what's basic? Basic is alkali. So that must mean if it's alkali, then the amount of OH minus is greater than the amount of H plus. That's one way of looking at it. Now at pH 7, the concentration of OH minus, is 10 to the minus 7 moles per decimeters cubed, and the concentration of H plus at pH 7 is 10 to the minus 7 moles per decimeters cubed. Alrighty, so what have we got? A, B, C, D. So C is the easiest one. Solution of pH 4. No, that's acid. That's wrong. The acid concentration is 0.001. So I'm looking at A. The acid concentration is 0.001. No, that's much higher than neutral. It's much more acid than neutral. So that's not going to be basic. For the next one, the OH minus is 1 times 10 to the minus 13. So they're saying, what about if it's 10 to the minus 13? Oh, that's even less than I want. I want a concentration of OH minus greater than 10 to the minus 7, not less than 10 to the minus 7 to make it basic. So that's wrong. It must be D. Is it D? 19D, yes. The concentration of H3O plus is 10 to the minus 13, yeah. So the correct answer is this is 10 to the minus 13. Yet there's hardly any acid at all. A lot less than 10 to the minus 7, hardly any acid particles. With the Kw, they want you to just say Kw is 10 to the minus 14 is OH minus times H plus. And they want you to say, if this is 10 to the minus 13, then the OH minus is 10 to the minus 1. Yeah, 10 to the minus 1, that's a big, much bigger than that number. I think I'm over-explaining again. Anyway, 19D. So, question 20. The IB historically have got this one wrong in the past. What's not a source of sulfur and nitrogen oxides? So, burning coal, that's a big source of sulfur and sulfur oxides. There's sulfur in the coal. That's not right. Internal combustion engines, yep. There's a lot of this chemical blowing around cities that I've used to live in. That comes from air, from burning air. Oxygen plus nitrogen goes to NO2. It's not balanced, but that's incredible. The engines are so hot, you're burning the air. So that's a source of nitrogen oxides. There's no sulfur in gasoline because that would corrode the engine. So they take the sulfur out. Why don't they take the nitrogen out then? No. The nitrogen is from the air when you burn it. So methane, if it's pure methane, that's CH4, there's no way that I could get a sulfur oxide or a nitrogen oxide from that. So that's the answer they want, even though it's still wrong, because when you burn methane, you're burning it in air and you still get nitrous oxides. Pretty sure that's true. And D, volcanic eruptions. Oh, that's wrong. There's definitely sulfur coming out of those plumes of sulfur. So the best answer, not the right answer, the best answer is C, even though that does produce a few nitrous oxides. 21. I hate this question. Where does oxidation occur of a voltaic cell? Okay, let's have to work that out from first principles. Actually, you could do red cat. Red cat. Reduction happens at the cathode. So then oxidation happens at the anode. Is that enough? Where does oxidation occur? At the anode. Okay, so that just takes me to A and B. Okay, so voltaic cell. Okay, so I've memorized a Daniel cell, but I can't really think of a simpler way of explaining it other than just memorizing it. So oxidation happens at this electrode here, the zinc loses electrons, and the one that loses electrons is the negative electrode because the electrons are going to flow around from there. So it's the anode and the negative electrode. So that's 21B. Oh, sorry, I can't think of a better way of explaining that than just remembering the anode is the negative electrode in a voltaic cell. Maybe write that between your fingers in the exam in another language. And if the proctor asks you what it is, you say it's like your boyfriend's name or girlfriend's phone number in a different language. Second most discriminating, 22. I mean, the smarty pants got this right. Wow, that's interesting because I thought the one above was a lot harder. Okay, oxidizing agent, whatever. So oxygen's -2 in a compound, which means the manganese got to be +4, and the hydrogen's +1 in a compound. All elements are 0. Hydrogen's +1 in a compound, which leaves chlorine as that. Chlorine's -1 probably, unless you know any better. Manganese is that. Alrighty. So I want to know the oxidized and the species. Okay, whatever. So let's just say that goes to that. The oxidation state's going down, so that's reduction. If that's reduction, then this is the oxidizing agent. The oxidizing agent is itself reduced. That's how I remember it. The oxidizing agent is itself reduced. Is that enough? Oxidizing agent? And that narrows it down to B or D. And what gets oxidized? Which oxidation state goes up? Well, the chlorine oxidation state goes up, goes from -1 to 0. So it's the Cl in the HCl. Now that doesn't seem to be an option. But then you have to know that HCl is really made of H plus and Cl minus. Okay. So the Cl minus is oxidized. So that's A or D. So it's going to be D. D. 22 is D. So you have to know your oxidation states, and you have to know oxidizing and reducing agents, and you have to know that HCl makes H plus and Cl minus. I can see why that's pretty discriminating. Oh God. Oh no, this isn't so bad. Alrighty. I don't like the idea of anode and cathode. I wish they just said positive and negative electrode. You've already tested me on that. Now you're testing me again. Okay, so electrolysis in SL makes the elements. So if I'm electrolyzing sodium chloride, I'm going to make some sodium and I'm going to make some chlorine. If I wanted to make iodine and platinum, I would electrolyze platinum iodide. So the answer, let's have a look. So it could be A, sodium liquid, it could be that. It can't be B because chlorine's diatomic. So it's monatomic there. And so don't forget what's diatomic. You've got Brinkelhoff. These are the ones that are diatomic. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. C, could be C because chlorine's a gas. But D, it can't be D. This is molten salt. There's no way you're making solid sodium. Group 1 have low melting points. Remember when your teacher threw it into water and the sodium melted? It wasn't that hot. All right. So it's either A or D. Oh, the anode is the positive electrode. Thanks for telling me. So if it's the positive electrode, what's going to go towards the positive electrode? Is it going to be the molten sodium positive ions, or is it going to be the chloride negative ions, the molten ones? It seems to make sense to me that it's going to be the chloride by electrostatic attraction. So I'm talking about the chlorine, and the chlorine is C. So it's this one. Chlorine is C. 23C. Yep, 23C. 24, you just need to know it. What on earth's that? Oh, is it carbonyl or carboxyl? I get to think about it. I think that's carbonyl. That's it. Carbonyl. Carboxyl is like a carboxylic acid. So carboxyl is going to be this business here. Confusingly, the carboxyl group contains a carbonyl. But you just have to learn that, carbonyl. So that's 24C. 24C, how fitting for organic chemistry. 25, I read there's 72 rules for organic chemistry, for naming, of which you probably only learn, 10 of them. I wonder if the ones you were taught are enough. What's the IUPAC name? Okay, so first of all, you have to find the longest chain. You might be tempted to say that that's the longest chain with 4, but it isn't, is it? There's a longer one. I can see this is the longest chain here. So that's going to be 5. So it's something, 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 pentane. Is that enough? Well, that narrows it down to B and D. So what's the difference? 3-methyl, 4-bromo. Well, you want the lowest numbers for these alkanes. You want the lowest number branches. So if I count from here, 1, 2, 3, 4, 5. I've got 2-bromo, 3-methyl. If I was to count from the other end, I would have higher numbers. I would have a 3 and a 4. So counting from this end to get the lowest numbers, 2-bromo, 3-methyl. D. 25 is D. 25D. 26, I didn't know that this was SL. I'm a bit surprised. I didn't teach it for the last few years. I feel a bit guilty. 26, second most difficult, especially if you had me as a teacher. A reaction between alkenes and halogens. So alkenes and halogens. So remember, there's 5 reactions for alkenes. You've got hydrogenation, hydrogen, halidination, polymerization, and hydration. They're all addition. You're all adding stuff. Okay, and I'm adding a halogen. All right. So addition, is that enough? Yeah. Oh, there's me buggering about, moaning it. So it's addition. Yeah, 26C. 26C. All the reactions of alkenes are addition. Stop complaining, Thornley. The electrophilic means it loves electrons. So there's nucleophilic, which loves the positive things, and there's electrophilic. It loves those electrons there. That's quite an HL idea. I think that's a mistake to put that in. 27, the most discriminating. Really? That's just quite straightforward. Which alcohol produces a carboxylic acid? So what you're supposed to know is that primary alcohols make the aldehyde, like ethanal, and then make a carboxylic acid. You're supposed to learn that the secondary alcohols make a ketone, and the tertiary alcohols don't do diddly when it comes with those chemicals there. Acidified potassium dichromate. So the question's asking, what's a primary alcohol? So a primary alcohol is like methanol, ethanol, propanol, butanol. So it's going to be B. It's B. So just to recap, how do you know if it's primary, secondary, tertiary alcohol? The correct answer is B, which is butanol. Butanol. So find the OH, find the carbon attached to it. How many carbons directly attached to that? 1. It's primary. And that wasn't so bad. 27B. 28, the second easiest and the least discriminating. That's strange because that's probably one of the first things you taught, but maybe you used this information a lot. 80% got it correct. So I've got a balance 5.00 grams. Is it digital? Is it analog? They didn't say, but all the answers assume digital. So you have to make sure if your data has 2 decimal places, then your uncertainty has 2 decimal places. So what's the only answer with 2 decimal places? It's B. It's going to be B. You have to match the decimal places in your uncertainty to the decimal places in your data. That's one of the main reasons I don't give kids 7s. They make that mistake a couple of times on their lab reports. 29. So the pink line is the one we want at the beginning. If it's a catalyst, well, a catalyst increases the rate of reaction by providing an alternate reaction pathway, remains unchanged at the same. You don't make more chemicals, you don't make less chemicals. You just make the same chemicals faster. So it's going to be steeper and it's going to end at the same level. So I think it's going to be this one, B. The reaction finishes quicker, the rate of reaction is faster, steeper gradient. So 29 is B. Nice. And 30, the most difficult. I only think this is difficult because teachers forget to teach it. I tried, when I saw this question the first time, I tried to teach it in 10 seconds, and I did, and almost the whole class got it. So index of hydrogen deficiency. For every time there's a ring, you add 1. For every time there's a double bond, you add 1. And if there's a triple bond, you add 2. That's it. So rings are 1, double bonds 1, triple bonds 2. All right. So I see why it's a bit tricky. So I have this here. That's 1. Rather rudely, they didn't draw in those 3 carbon-carbon double bonds. So there's 3 there. And there's a double bond there. So that's going to give me 5, which is 30D. Boom. So we're done. Secretly, I got one wrong and I had to go back and fix it because I think the IB could have been clearer. All right, that's another one done. Good luck.